SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustions, Module 2 Entropy and Exergy. So, in this module we have covered entropy analysis and also partly exergy analysis. In today's class we will again discuss about exergy analysis part 2, and in fact it is the last lecture of this module. So, in this lecture we will briefly discuss about exergy of the closed systems, which we have covered in that previous lecture. Then moving further, we will discuss the exergy rate balance for a control volume. So, for initially we started with closed systems, then we will move to control volume. Now, on this basics we will introduce another concept, what we call as a second law efficiency. Many times it is also referred as exergetic efficiency, and towards the end we will try to make a comparison what is energy and what is exergy, how they are viewed while doing the thermodynamic analysis. So, let us start this lecture. We have already covered the exergy for the closed systems in our earlier lectures. In order to give the brief introductions, I can note down the following points, that we all know that exergy is a thermodynamic property and it is an extensive property. It is a measure of departure of state from the system with respect to environment, and it is interpreted as maximum theoretical value of work from a systems, and it is regarded as the thermodynamic property like energy. Now, in some situations when there is a work input to the systems, in that sense we can say that exergy is regarded as the magnitude of minimum theoretical work input or required to bring the systems from the dead state to given state. Or in other words, when you say the system moves from its original state to dead state, it produces work output. When it moves from dead state to a given state or any arbitrary state, then it is the work input to the systems. Now, with this concept, the second law of thermodynamics views this as a decrease in the exergy principle. So, in the context of entropy, where we say is that entropy of universe always increases. So, in that sense we call this as an increase in the entropy principle. In similar way, we can also view the exergy principle as decrease in exergy for the universe. Now, why we require exergy? Because the systematic evaluation and comparison of energy and exergy introduces the concept of exergy auditing for various thermal systems. In our previous lecture, we derived the expressions for exergy, that means any systems which is at initial state which is at any arbitrary initial states with internal energy U, volume V, entropy S with certain kinetic energy and potential energy, then exergy for that systems can be considered with respect to environment, for which the environment is in dead state, or this when the system moves from its arbitrary state to dead state. When it reaches the dead state, or in other words, it is the ambient or surrounding pressure and temperature, which is P naught and T naught. At that point, the dead state will have internal energy of U 0, volume V 0 and entropy S 0, and the difference between these numbers will talk about exergy for the systems when it goes from a given state to a dead state. Similar way, we can define the specific energy, we can find out the exergy transfer, and we can get the exergy steady state exergy balance. Or in other words, if you look at this exergy transfer, we mainly concentrated about the heat part, because this heat is a low grade energy, and complete conversion of low grade energy to high grade energy is not possible. Now, when during this conversion, you can see that there is a ratio 1 minus T 0 by Tb. Tb is the boundary temperatures. For example, if we can say that there is a system which exchanges heat to some environment. So, Q dot J comes from as a heat into these systems T j, which is greater than T o. So, ambient temperature is T naught and pressure is P naught, and if this is the energy transfer, the corresponding exergy transfer would be, we can say 1 minus T 0 by T j. T j will be the boundary temperature, and this into Q j. So, you can see here, although the exergy energy is Q j, but there is another term which is multiplied 1 minus T 0 by T j into Q j. This is about, this information is about exergy, and this information is energy. Okay. So, this is what the main difference when you deal with energy and exergy for a closed systems. Now, we will move to the exergy rate balance for a control volume. So, now when I dealt with a control volume, I can say that both energy transfer and mass transfer is possible. That means, we can schematically represent a control volume, and in which certain stream is entering at that means certain mass flow rate is entering into the systems, we say inlet I, and some mass flow which goes out, we say m dot E. Now, in this process there could be heat transfer, there could be work transfer. So, there are a lot of possibilities. Now, for each situation and the and for this mass flow rate, there may be the flow velocity which is entering V 1, and the flow velocity which may be leaving is V 2. Okay. It may have internal energy U 1, U 2, okay, and its elevation could be Z 1 and this could be Z 2. So, all these possible terms can be included, and apart from that, when you do the analysis of exergy, we need to think about the surroundings or environments, and this environment condition is normally referred as P naught 1 bar, T naught 300 Kelvin. Now, for this control volume, we can find out time rate of change of exergy dECV by dt. This could be with respect to heat, with respect to work, that means work transfer to the control volume. Here also we will have another expressions, because when there is a work transfer, there is a another resistance to this workflow, that is from the surrounding or environment, and this particular terms comes by virtue of the flow, and this is the this E d dot is Exergy destructions. So, first term refers to heat, second term refers to work, third term refers to flow in or mass flow, mass transfer into and out of these things, and last term is the Exergy destructions. And these equations can be reduced for a steady state where d Cv by dt is 0, and we can write that expression. Subsequently, in this case we can see that there could be multiple number of inlets and multiple number of outlets, for which we have summation of phi or summation of E. Now, if there is a single inlet and single exit, then this information will come in the form of enthalpy, okay, for unit mass. Then in a compact form we can rewrite these expressions, and subsequently single inlet and single exit we write these expressions. So, finally, end use of your Exergy rate balance for the control volume can be expressed by this last expressions, where we have to find out EF1 minus EF2, that is Exergy due to mass flow at inlet and outlet. In fact, these are the working formula to be used for solving the problems. Now, the concept of Exergy also introduces another term, we call this as a second law efficiency, and mostly this we will try to interpret with respect to an closed systems. And as you refer in this particular figure, we are going to try, we are going to see that how for a closed system how energy and Exergy can be related. So, for that let us see this particular figure. We have a system, it has a boundary, system boundary. Now, there are some source of heat which is available in the form of air or fuel mixture, and this heat we are going to utilize in a suitable form. So, I will say that Qs, that means on this, for this systems, the from the left side of the surface, which is maintained at surface temperature Ts, it interacts with this air fuel mixture, that for which heat enters to the system is at a rate Q dot S, and in the another side of this closed systems heat leaves out for its utilization, and this temperature is maintained at Tu. So, this is something like we have a Carnot cycle which is similar to what one is source and other is sink. So, we have here we have one temperature is Ts, other temperature is Tu, and in this process you get Qs dot as input and Qu dot output. But apart from this, when you do the Exergy analysis, we really in fact when you do the energy analysis or in the second law analysis, this was viewed as a situation where environment is not taken into account, loss of heat to the environment is not taken into account, or in other words you do not really exactly quantify how much energy that is lost to the surroundings or environment due to irreversibility. So, for that another term is used here, which is Q1 dot, and this Q1 is nothing but the energy lost to the surrounding by heat transfer at a rate Q1, and it is this heat loss is happening at a surface temperature T1. Now, we assume that the system operates at a steady state, so that there is no work, and so that we can write down the closed system energy and Exergy balance equations. So, if you look at this particular figure, one angle we can write this rate of energy change with respect to time, dE by dt is difference of heat minus work, and since we say there is no work transfer, so this term vanishes. and when there is a steady state, dE by dt also goes to 0. So, this expression becomes Qs is equal to Qu plus Q1. So, this is simply the energy balance. Now, we are going to look at what is the Exergy balance. So, in fact, when you deal with the Exergy for same term dE by dt, which is we will interpret as Exergy, because E is your energy, we view this as a dE by dt, but same E when you interpret as a Exergy, here we will have the Exergy term which is associated with each of this heat transfer. So, first one is Qs, which is the input to the systems, corresponding Exergy value we can have this, and for the Qu the corresponding Exergy term or rate of Exergy term will be this, and for Q1 the corresponding Exergy term is this. So, what we look at from this expression is that for each of the term the ambient temperature was taken into account. So, I can say although this is a system working systems, your ambient conditions we can have P naught and T naught, and that we say the surrounding temperatures. Now, in this process of this is what we do for heat transfer. Now, the system also could do some work transfer. So, that work transfer comes in this form. Now, in our closed system situations when there is no work, so this term can vanish, and steady state this term can vanish. After even here dE by dt is also 0 for the steady state. Now, by neglecting or these terms and rearranging these expressions, we arrive at the expression for Exergy. So, in fact, if you look closely between this energy relation and Exergy relations, you can find out that in the Exergy relations there is a corresponding term 1 minus T by T naught by T that comes into picture. Apart from that, there is another term ED which we call as rate of Exergy destructions. So, the second law of efficiency talks about that although we have energy gets balance is taken into account, but not necessarily that Exergy will be balanced. So, that is what we say that Exergy is a non-conserved property. Now, let us move further what the second law of efficiency talks about. So, when you deal with the first law of efficiency, in fact, in the Carnot cycle, just while discussing about the Carnot cycle or during the second law analysis, we say that the efficiency term is Qu by Qs. Now, with respect to this particular term, what is Qs, which is input to the systems, and Qu which is heat getting utilized. So, that is Qu by Qs. So, for this closed systems, of course, there is no work transfer here, but so we can say efficiency calculation is this. Okay. Now, if I want to calculate the exergetic efficiency, then we have to recall the same expression of efficiency, but we are going to write in a different way. That means, for this Qu which is heat as a energy, corresponding Exergy value will be 1 minus T naught by Tu, that where T naught is your ambient temperature and Tu is the temperature of the surface at which heat is entering, Qu is entering into the system. And similarly, for Qs, which is the input for the system, corresponding Exergy term would be 1 minus T0 by Ts, and here Ts is the surface temperature at which the heat is entering into the systems. So, if you simplify these expressions, we will find this Q by Qs is efficiency. So, exergetic efficiency epsilon is function of efficiency and the temperature of surroundings, temperature of heat getting surface temperature of at which heat is being rejected or utilized, and surface temperature at which heat is entering into the systems. Now, if you look closely to these expressions, some more information we can gain, that is the if you try to plot the T1 by T0 as a function of the corresponding exergy. What it says is that the heat loss in terms of exergy depends significantly on temperature at which heat loss occurs. So, initially it starts increasing and it keeps on increasing, because that means heat loss also increases significantly with respect to temperatures. That means, if a body is at higher temperature, heat loss will also be more and more. Second point is that it should be emphasized that when you find the efficiency value, we can say it is QE by QS, and there is a possibility that all the heat can be, if all the heat gets utilized as if we have Carnot efficiency, then that means from the first law it says that all the heat gets utilized, but that in reality that does not occur, which means that there is something difference that drops in while calculating the energy. So, where it goes, that we found out based on the source temperature T s and end use temperature T u. So, they are function of exergy calculations. Another information we can gain here, that the exergy efficiency is always less than unity, because in most of the situation your efficiency is also less than unity. So, obviously, when you multiply this term which is less than unity, exergy efficiency will also be less than unity. So, having said the second law efficiency, we can really calculate the exergetic efficiency for some steady flow devices or components or thermal components. In the second law analysis of entropy, we discussed about the thermal components like turbines, compressors, heat exchangers, pumps, nozzles, all these components we have analyzed, and for them the one way to interpret is through their isentropic efficiency. But having using that term isentropic efficiency, we really do not account how much, how much heat is lost to the surroundings, or what is the contribution of irreversibility in the systems. So, while talking about entropy, it just talks about maybe isentropic efficiency, it only talks about the internal reversibility analysis, but it does not talk anything about the irreversibility part. So, for this irreversibility part, exergy calculation is very vital, for which we call this as a exergy auditing or the proper utilization of energy resources. So, based on this component, based on this concept, we define exergetic turbine efficiency. So, when you say turbine, it is a work producing device. So, the work term that means work flow per unit mass is in the top. In the bottom part, we have difference in the exergy due to flow in and flow out. Similarly, for pump case, work is input to the systems. So, that means it is in the denominator and with a negative side, and exergy in this case drops. Okay. So, there is a decrease in the that means there is a decrease in the flow exergy for turbine from inlet to exit, and there is a increase in the flow exergy from inlet to exit for compressor and pumps. Another very vital part is about the exergy calculation for heat exchanger. In fact, heat is the source for which complete conversion is not possible. So, exergy calculation is very significant in this in terms of second law efficiency. So, heat exchangers can have of two types. First one is a counterflow type, in which there is a hot stream entering and hot stream leaving, condition 1 and 2, Another way is, there is a cold stream entering and cold stream out, and both the fluids, hot fluid and cold fluid, they do not mix. So, for each streams we can find out the Exergy expressions due to this cold fluid and hot fluid. When we use a direct contact exchanger where both hot fluids and cold fluids mix together and they move as a they come out as a common stream, then Exergy calculation is little bit different. So, you can say that means we have to find out Exergy for the either for the cold stream or hot stream. So, in that way we can rewrite these expressions in the form which that means in terms of 3, 2 or and 1 and 3. So, this is how we interpret Exergy for heat exchanger calculations with mixing and without mixings. And the last segment of our discussion today, in fact for this module, is energy versus Exergy. So, we have given all the concept of thermodynamic concept starting from zeroth law, first law, second law, Exergy, entropy and Exergy. After doing all the analysis, the very fundamental difference that still lies is that why we require Exergy. Although energy analysis gives sufficient information, why we require Exergy? The word used, when you use the word Exergy, we basically do energy auditing, and in fact when you use this energy, we really do not bother about the surrounding conditions. And in fact, in some situations energy is available in variety of forms. It can be from fuel, it can be from solar energy, it can be from wind energy, for variety of sources, and but its proper utilization with a particular components needs attention. So, as you can look for this particular figure here, where I am just giving some benchmark or standard numbers. In fact, it is a work producing device, or it is a, we can say as if we have a thermal power systems which is producing a work or shaft work, and in which we are supplying some flow that enters into the systems and some flow that goes out of the systems. And through this process, and in this, in fact you can say it is a control volume analysis, and there are possibility of work transfer, and I will say that I will give some numbers that work is heat is being supplied to the systems is, for example, it is 90 kilowatt, and apart from that there is also some mass flow which enters to the systems. It gives when energy into the system as 10 kilowatt. So, if I say that how much energy we are pumping into the systems, then we can say one is 90 kilowatt by heat transfer and 10 kilowatt through this mass transfer which is through inlet. So, total 100 kilowatt energy is being supplied. So, when you do the first law analysis, in fact most of the things, that means we will find out that entire work can be calculated. Some work can be calculated as let us say 40 kilowatt through the shaft power, and something which goes out is 60 kilowatt. So, we can say if it is efficiency, we have say 40 by maybe 100 kilowatt. So, 40% efficient. But most of the things, if you say that energy balance is taken into account. So, energy auditing, it is a clear 100 is input and 100 is output. Now, let us calculate the or let us evaluate the Exergy values for these heat transfer modes. First thing, we have QCV which is in Exergy transfer as a heat which is 90 kilowatt, and if you use this for the Exergy corresponding Exergy value with surrounding temperature maybe T naught as 300 Kelvin and P naught as 1 bar atmospheric pressure, then we can find out its value could be maybe 60 kilowatt. Although we give 90 kilowatt of energy as a heat, corresponding exergy value is only is 60 kilowatt, which is entering. Even for the mass flow, it was 10 kilowatt, corresponding exergy value for the exergy value with respect to flow inlet, which is can be calculated from this expression, is about 2 kilowatt. Just to say that these are just gross numbers. More accurate numbers can be found out with putting appropriate values. Okay. Now, then moving further for work transfer, and of course, we say that work is a complete conversion of work is possible. So, we can say work transfer, corresponding work transfer will be same. Exergy with respect to work transfer remains same, and exergy with respect to flow that goes out, it was 60 kilowatt, but it is 15 kilowatt. But ultimately, when you recalculate, we supplied energy 100 kilowatt, but its corresponding exergy value, total exergy value is about 62 kilowatt, and the exergy that comes out, it was 100 kilowatt, but it is now 55 kilowatt. So, basic difference lies here, that 100 kilowatt becomes 62 and 55 by taking into account of surrounding temperatures and pressure. So, if you see here, there is exergy in, there is exergy out, it is not balanced. So, it is not a conserved property, but and exergy is destroyed from this process, we can find out 7 kilowatt, which is nothing but your ED, and this amount is destroyed due to irreversibility, and it is also recoverable. Why this analysis is important? Because that when you design a thermal systems, apart from energy analysis, we must do the exergy analysis, that when you design these systems, you have to do such a way that there will be minimal destruction of exergy. That means 7 kilowatt number should be as small as possible, so that effective utilization of resources can be taken into account. So, this is how the importance or significance of exergy is realized, because exergy gives a sharper picture of performance than energy, because it includes the irreversibility. Before I conclude this lecture, let me discuss some numerical problems pertaining to this particular lecture, and it was mainly targeted for exergy balance for a control volume. So, we will try to see that how we can use the fundamental equations for exergy calculation of some thermal components. The first component is a throttle valve. So, you all know that there is a throttle valve is a valve which regulates the flow conditions which is entering into a system or medium, and through this throttling process, the thermodynamic parameter that remains constant is enthalpy. So, here the problem that is given, that we have a throttle valve which is kept into this into a medium. So, the valve opens and closes. So, the some steam which is entering, it is a superheated water vapor. So, it is at 30 bar 320 degree centigrade. So, condition is P1 and T1 is given to us, and when the valve opens, it allows this flow, and the stream leaves at P2 is equal to 5 bar. So, this thermodynamic process we can say enthalpy remains same, which is H1 is equal to H2. Now, we were going to get the conditions that, and apart from that we can say ambient or surrounding is at 1 bar and 300, let us say 20 degree centigrade, 293 Kelvin. Now, our calculations what we require is exergy destruction per unit mass of the flow streams. So, before you start, these data are given for superheated water vapors. So, we can use steam table. Initially it was a superheated state. For these conditions we can find out from the steam table what is enthalpy. H1 as 3043.4 kilojoule per kg. We also require entropy S1, this value is 6.62 kilojoule per kg Kelvin. Now, what remains H2? Enthalpy remains same. So, for P2 is 5 bar and H2 as same as H1. We can find out from steam table for these two situations, these two data, the temperature would be in fact not required temperature, entropy is required. S2 would be 7.42 kilojoule per kg Kelvin, and for also you can also calculate temperature, but for this question temperature might not be required. So, you have all the informations, then we have to recall, and of course, here we can say Q dot CV is equal to 0 because there is no work transfer and no heat transfer, and no data is given about the flow velocity. So, with this we can recall about the steady state, energy exergy balance, which says that 1 minus TO by TJ into QJ minus W dot CV plus M dot, that is due to flow, EF2 EF1 minus EF2 plus minus exergy destruction E dot D is equal to 0. So, this part is 0, this part is 0, that is and this equations now becomes E D dot by M dot, which is nothing but exergy destruction per unit mass would be EF1 minus EF2, that means exergy transfer due to mass flow rate. We can further rewrite as H1 minus H2 minus T0 into S1 minus S2 plus V1 square minus V2 square by 2 plus G into Z2 minus Z1. So, this term vanishes because we have no information. By putting this value E D dot by M dot, we can calculate as in fact H1 and H2 are same, they will vanish. So, it will be minus T0 into S1 minus S2. So, S1 minus S2 we can put these numbers. So, and T0 is 293 Kelvin. So, this number will come about 234.4 kilojoule per kg, which means that this throttling valve, due to this throttling valve, the exergy destruction is 234.4 kilojoule per kg. So, we all know that throttling process is an irreversible process. So, this is taken into account or proved, and why it is a irreversible process? It is mainly due to uncontrolled expansion. So, I will put this uncontrolled expansion. If you see that the steam expands from 30 bar to 5 bar, but this is expanded in an uncontrolled manner through a throttling device. Due to this uncontrolled expansion, there is a irreversibility comes into account, but this uncontrolled expansion can be a control be put in a control mode through an expansion in a turbine process, which may be considered as internal reversible process. Okay. Now, we will move to next problem, where it is a very common problem which you use in a gas turbine engines, and this gas turbine engine we use some kind of a compressor in which the flow enters into an heat exchanger and the air gets preheated through combustion products. So, the typical arrangement could be like this: we have a counter flow heat exchanger. In this counter flow heat exchanger, schematically if I write, there is some flow which comes in, and the hot fluid and the cold fluid, they come in a different path. So, first fluid that goes, we say compressed air, and it enters to this heat exchanger and it leaves. So, initial condition of this compressed air is 10 bar. So, P 1 is 10 bar and T 1 is 610 Kelvin, whereas P 2 it leaves at air leaves at 9.7 bar and 860, and T 2 is 860 Kelvin. Then, so you can put this as a condition 1, condition 2. Another stream that enters, that is at state 3 and leaves at state 4. At state 3, the conditions are P 3 is 1.1 bar, T 3 is 1020 Kelvin, and P 4 is 1 bar. Apart from that, we surrounding say P naught 1 bar and T naught is 300 Kelvin. So, these data are given to us. So, the surrounding conditions and is condition of these things. So, first thing what we require is exit temperature of combustion gas. So, basically all the temperature is known except the condition 4. So, we can first analysis we can do energy analysis or energy balance. Since it is a very simple systems, we can write m dot H 2 minus H 1 is equal to m dot H 3 minus H 4, and H can, since it is a compressed air, H can be represented as Cp times T 1. Now, by putting this by taking Cp as 1.005 kilojoule per kg Kelvin, then we can find out and m dot will get cancelled. We can find out T 4 as 770 Kelvin. All the numbers we know except T 4. So, T 4 is now 770 Kelvin. Second analysis, we are going to find out what is the net change of flow exergy from inlet to exit of each streams. So, flow exergy from inlet to exit when you for each stream, that means we have to calculate separately for one for stream of compressed air, other for the stream of hot stream. So, that means it can be divided in two loops, one is for the between 3 and 4, other would be on 1 and 2. So, first one if you calculate for 1 and 2, state 1 and 2, if you want to calculate, we can write m dot E f 2 minus E f 1 is equal to m dot H 2 minus H 1 minus T 0 into S 2 minus S 1. So, this is what we say flow exergy from inlet to exit for compressed air. Now, from breeze we have to calculate the each terms this we know we can find out H 2 minus H 1 as C p times T 2 minus T 1. So, this number we can find it out as 251.25 because all the numbers T 2 and T 1 is given. Now, T 0 into S 2 minus S 1 would be, so it is a entropy difference. So, here you have to take the entropy data with respect to entropy at a reference state. So, this is equal to S 2 at reference state minus S 1 at reference state minus R bar by M into ln P 2 by P 1. This has to be evaluated at temperature T 1 and T 2, and these numbers we can get at S 2 maybe 860 Kelvin. This value is 2.8 kilojoule per kg Kelvin. So, this will get data table. In any thermodynamic book we give you at temperature 860 Kelvin, entropy value is this. Similarly, at temperature T 1 is T 1 at 610 Kelvin, your entropy values would be 2.4. Apart from that, we have R bar, universal gas constant, 8.314 kilojoule per kg Kelvin, and molecular weight simply we can write 28.97. By putting these numbers we can now calculate for the question B, part B, m dot E f 2 minus E f 1 would be 100. M dot is your 100 kg per second, and this E f 1 and E f 2 would be 2 is 51.25 minus the second term that involves T 0 into S 2 minus S 1, this number is 122.6. We can get this value is 12.865 megawatt. And similarly, you can repeat it for state 3 and 4. We will find out m dot E f 3 minus E f 4 as m dot H 4 minus H 3 minus T 0 S 4 minus S 3 minus R ln P 4 by P 3. So, data that is required is T 3 1020 Kelvin T4 770 Kelvin, corresponding entropy 2.99 kilojoule per kg Kelvin. S3 corresponding entropy is 2.69 kilojoule per kg Kelvin. So, we know these numbers. R we know R bar by M. P4 you know one is P3 is 1.1 bar, P4 is equal to 1 bar. By putting all these things, we can find out m dot EF3 minus EF4 is equal to minus 34.95 megawatt. Now, so this is for the state 3 and 4, and last part of the analysis, rate of Exergy destruction. So, the rate of Exergy destruction we can say E d dot is equal to m dot EF1 minus EF2 plus m dot EF3 minus EF4. This expression we get again from Exergy balance equation. Exergy balance equation by neglecting terms of work transfer and heat transfer. Now, when you put these numbers, but we have calculated in a reverse number. So, this number we can rewrite as E d dot is equal to minus 12.865 and here it will be plus 34.95. So, this is 22 megawatt. It's roughly about 22 megawatt. So, this analysis tells that we are talking about inflow Exergy numbers about 12.865 and 34.95, but we are losing 22 megawatt of Exergy. So, this means that substantial Exergy is destroyed. In other words, loss of energy is much higher due to irreversibility. So, this needs attention that we should design a better counter flow heat exchanger which can still further reduce this number from 22 megawatt to still further by considering the proper methods where the loss of irreversibility can be minimized. So, with this background and concept of energy and Exergy, I conclude today's lectures and also I conclude module 2. Thank you for your attention.